This is a very quick video on what logistic growth is and some definitions for it. So logistic growth is a type of a function, a logistic function, that helps us understand population growth over time. The reason why we use logistic models for population growth over time is that exponential models work very well in the short run, but they tend to not make much sense in the long run because population models tend to have some sort of restrictions, like how much land mass there is or how many resources there are to sustain things. And so you can't have deer populations continue to grow exponentially forever, or people populations, or ant populations, or bacteria populations, or what have you. They can't grow exponentially forever because we run out of space or we run out of food for things. And so there's some sort of restriction that ends up happening on it. And the logistic growth model helps us understand that. So I have a logistic model that is being graphed. And so what we're going to do is we're going to take a look at what each of these things kind of does. So whatever my C value is up at the top of my function refers to the carrying capacity. So that's something that we approach but never quite hit. And so even though this says 400 right now, it's actually 39.9999999, something like that. And so what happens is my function gets really close to that, but that's an asymptote for my function. So whatever my C is, that is what is called the carrying capacity. So notice that the function gets really close to that, but never quite hits it in terms of population. And so what's happening is our population gets, that's basically the cap of the population. So this area won't support more than 200 deer or something along those lines. So if I extend this to be a lot bigger, my carrying capacity can get a whole lot bigger. It's not like there's any sort of problem with a large C. So my carrying capacity can be very big. But that's basically what that C represents. That represents the peak amount of population that we can possibly have. Now, this A value changing will dictate what my population starts at. So notice with A equals 7 here, notice that I have C over 1 plus A. That's my initial time value. That ends up being what my population starts at. So that ends up being 1960 over 8. And so depending on what my values are, this can be how my function starts. Finally, there's also this K value. The K value, the smaller it is, the slower the growth is. So notice that the growth ends up being a little slower. It takes longer to get to the carrying capacity. Whereas if my growth rate is faster, the K is higher. So this gets to the carrying capacity much faster. Slower, faster. So those three things are the things that we really have to be aware of. C represents the carrying capacity. So the carrying capacity is the largest possible population. C over 1 plus A represents the initial population. And that makes sense because when t equals 0, what happens to e to the negative kt? That would become 1. So C over 1 plus A is what would happen if t was equal to 0. And then K represents my growth rate. Larger K means faster initial growth. And then we get closer to the carrying capacity earlier on. So that's what's happening with this logistic growth model.